the topics will be in such order. First is moment of inertia, MI. That's the first topic. What is exactly in that? We will know later on. Second is L, that is angular. This MI is moment of inertia. This is angular momentum. Then we will have these are the topics in order. First moment of inertia, then angular momentum, then rotational energy. Oh, sorry, I forgot one of them, and that is torque. Okay, so moment of inertia, angular momentum, torque, and rotational energy. These will be the topics. Fine. Let's start with moment of inertia. Mind you, what is meant by inertia? Now, let's say if a body is moving on a ground. So, if a body is moving on the ground, inertia says that it will continue to be moving in the same direction with the same speed on the ground. Now, you might say, but we don't see really if they always stop. That's because now comes a criteria that this will happen only when there is no external force. If there is external force, that will either change the direction or the magnitude or maybe even both of them also. So therefore, first law is essentially inertia law. A body in motion will continue to move and a body at rest will continue to be at rest. Same happens in rotation also. In rotation also, a body in rotational motion will continue to move in rotational motion. Whereas the body which is at rest will continue to remain at rest. But the point is that, yeah, resistance to change. That's a good way of saying. Mithun has given this answer. That is, inertia is what? Resistance to change. Now, resistance to change is not only for linear motion, it is also for rotational motion. When you switch off the fan, so let's say the fan is rotating like this, you switch off the fan. Does it stop? No. It goes on like this, and then it slows down and slowly, and then finally it comes to rest. That is because it wants to continue to rotate due to inertia, but because of friction, air resistance, all those things, so bearing and all that is there in the fan, they oppose. So therefore, they finally manage to stop the fan. Otherwise, if there is no opposition, then it will continue to rotate. Just like the Earth is rotating for the last billions of years, and it is still, spinning, isn't it? That's because there is nobody to stop it. Whereas in the fan, there's air resistance, there's a friction in the ball bearings that is there in the fan, friction between the blades, and so on. And all of these lead to what? The fan stopping. So it's okay, we understand that yes, something can stop and something can start also. Point is that I want to know the resistance to change. Now, in case of linear motion, inertia quantity is mass. Okay? So we know that in linear motion, so if mass is more, that means in linear motion, inertia quantity is more. My question now is, what should be an appropriate? So look at the theme of the question. What should be an appropriate measure of rotational inertia? Got it? So question is, what should be an now, you know what, when this question came to the mind of scientists, look at how they thought. What they started thinking was like this, that why not have some very fundamental quantity and use that as some kind of a correlated thing, to find out the inertia quantity in rotation. Is that okay? Now, for that only, scientists finally defined what is called as moment of inertia. That is the measure of what is called as moment So what we want to now understand is, yeah, I've already started getting the answers because some of you might have already read the topic. But you know what? There are answers coming up that moment of inertia is actually equal to mr square. Very good. But my question is, why they have selected mr square? Why not mr cube? Why not mr to the power 7? Why not mr to the power 2.5? Mr to the power 3 by 2? And so on. Why is it that they have selected, moment of inertia or mr square as the quantity? That's because energy is used to connect them. Because there is something fundamental in energy which transcends the barrier of topics and so on. In linear energy, that is kinetic energy, we know that energy is equal to half mv square. Let me write it slightly differently. Let me write it as half into. So linear energy can be visualized as half linear inertia parameter into now let me remove all this. Into just have a look how I'm trying to define the definition of energy. Now you might so what? You might say so what? You know what? Now I'm going to analogously do a similar thing. For example, let's say there's an object which is tied at a distance r, and let's say it is rotating with an angular speed of omega. So therefore the velocity of the speed will be equal to omega. We know that. So what is the kinetic energy now? The kinetic energy is half m Now you know what? Scientists thought, okay, now let me write it like this. Half rotational into rotational motion. Now compare. If I compare, what I'm seeing is that moment of inertia should be defined as what? So this is the rotational inertia parameter. So that way, if I look at, then the inertia should be written as m into r square. This one. Sorry, this one. M into r square. That's how today we will say moment of inertia is equal to m into r square. Okay? But you know what? This is too simple a question. But sometimes it will happen that maybe I'm having a slightly more difficult question to handle. And that is, what would happen? Let's say if there is a distributed mass. For a distributed mass, what we will do is that so this is actually mr square. The quantity moment of inertia is actually equal to mr square, and this is equal to r square dm. Instead of mr square, we will take up smaller sections. So let's say this small section, this is distance r. Find out the moment of inertia of this disk. So in that case, what will I do? I will take a small mass and integrate. Okay. Now there's a question from Bhavil, and that is, can you please repeat what you said in the last 2 minutes? See, what I'm trying to say is that in rotational motion, the moment of inertia, the inertia quantity is mr square. Where did I get it? See, on comparison we are getting. On comparison, we are getting that one. So if it is a point mass or a collection of point mass, then just go on adding the mr square, mr square, mr square values. But if it's a distributed mass, so this will be used in distributed. ठीक है, देख लो बड़ा अच्छे से. अब इसको यूज कैसे करेंगे? दैट्स बड़ा सिंपल है. तो मैं कुछ क्वेश्चन देना चाहता हूं. हैव यू नोटेड एवरीथिंग? थोड़ा नोट कर लो जरा. Bhabil Kumar has said, please repeat the comparison. See, what I'm trying to say is that when we write kinetic energy in linear motion, it is half mv square. Now that can be imagined as half linear inertia and motion ka square. है ना? So the linear inertia therefore becomes mass. Now let's calculate similarly the kinetic energy in case of rotation. So in case of rotation, the kinetic energy becomes half m, this is mass, into omega r ka whole square. So that is equal to half mr square into omega square. That is equal to half of what? This part, that is omega into m square. This omega square is of course the rotational motion parameter. So if I compare, you will see. If you compare, you will see that in case of point mass, it is mr square, and in case of so in case of rotational motion, you can see that by comparing, we are seeing that rotational inertia parameter becomes equal to what? Mr square. So for large number of particles, okay, Tejesh has asked why R is not considered as dr. Well, actually, you know what? Let me draw the figure again. That would be better. You know what is happening? What is happening is that if this is the body, and let's say this is the axis about rotation, half we take a distance as small r, and this mass as dm. So the velocity is omega into small r. Omega r होता है, तो half m ठीक है ना? Now if I let's say apply integration, because I have to do it for all the particles, so the expression will be like this, that therefore the kinetic energy will become equal to total kinetic energy, Tk, will be half therefore using this, and of course omega square is there, that's where the r squared dm came. Okay, there is a doubt also from Samaksh, and that is 15 and 20. Why don't you send the question paper in the WhatsApp? Okay, somebody has done it, it seems. This is who is asking the doubts? Samaksh. Aditya has asked, is R the radius of motion? Well, you know what? R is different for different particle. For example, for this particle, R is this. But for some other particle, let's say this, R is this. So R is the distance of any particle as such. For another particle, R is this, dm. For another particle, R is this, dm. Okay. Fine. Now, just a few more minutes. Let me just take a few more minutes to explain this concept. For example, now let me ask you a question. Distributed mass we'll do next class, but at least do one or two questions based on point mass. Mind you, an object can be rotated in a variety of ways. And for each way, there will be a different moment of inertia. So let's say there is a mass here, there's a mass here, there's a mass here, and there's a mass here. M, 2m, 3m, 4m. Suppose I rotate this object with an axis like this. So you have to find out the moment of inertia when I1 is the axis. You also have to find out the moment of inertia when the body is being rotated about this axis. You also have to find out I2. And lastly, by the way, these are all, this is 3m, 2m, m, 4m. And these are L, 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 L. This is I2. And lastly, this is I3. Okay. Now what is the I? Oh, please switch to previous board. Yes, I've just done it. I mean, can we compress it? I don't think there's a zoom facility out here. But there is a zoom. No, there is no zoom. Okay, I'll just switch to previous board, I mean, which I've done just now. Samaks, have you copied? Okay, you have to find out the moment of inertia. No center mass this time. Moment of inertia, if it is rotated about I1, if it is rotated about I2, and if it is rotated about I3. So this is your I3. See, the point is that, I mean, let's say if this is that object, I can rotate the object in a variety of ways. So let's say this is I1. This is how it is rotated. I can also rotate like this. So this is I2, let's say. I can also rotate I3 like this, center. Or it could be also diagonal. Just have a look. So there are many possible axes. And for each axis, there will be different moment of inertia. Find out for I1, I2, and I3. In general, you will get it because the masses are m, 2m, 3m, 4m. And the lengths of the squares are given L each. Accordingly, to find out I1, I2, and I3. Okay, there are some doubts also. Let me quickly solve this so that I can take some of the doubts. First question, I1. I1 is this, that, I1 is this, I2 is this, and then I3. Now, in case of I1, there is no contribution of moment of inertia. In case of I1, there is no contribution of moment of inertia due to 3m mass and due to 4m mass. Why? That is because both of them are on the axis itself. So therefore, I1 will be 3m into 0 ka square plus 4m into 0 ka square plus m into L square plus 2m into L square. So it is 3m L square. This is I1. So I1 is done. What about I2? I2 will now be so I2 will be equal to plus 0 square so that will be equal to 7 ml square. Why is it so? That's because when you are finding out I2 means you are about to find out the moment of inertia for this axis. Now in this case 3m and 4m are very important. So 3m into L square plus 4m into L square plus 0 square. This is that of the this is the contribution of the 2m and m mass. No contribution at all. So that will be equal to what? 7 ml square. Now what about I3? In case of I3 there is something interesting, and that is in case of I3 the moment of inertia of this is not to be included, this not to be included, this is to be included, because see here this is what. So I3 equal to ml square. In this case it will become अच्छा कर देना भूल गया, चलो कोई नहीं. And 4m, हाँ कोई बात. So I3 will be equal to 3m into L by root 2 ka whole square, because mind you this is of course root 2L. This is also the entire thing is root 2L. So what I need is this one, and that is actually equal to L by root 2. So 3m into L by root 2 whole square plus 4m into 0 square plus m into L by root 2 whole square plus so that will become equal to 3 by 2 and 3 by 2 and half. 3 by 2 plus 1 by 2, that is 4 by 2, yani equal to 2 ml square. Just have a look. So the first answer is of course 3 ml square, then it is 7 ml square, and that is lastly 2 ml square. How L by root 2 came? Tejas has asked, is it rotating through the diagonal? Yes, it can. So I3 is actually diagonal axis. I3 is now those are the answers. 2 ml square. Then one answer we had 7 ml square. So the answers are 3 ml square, 3 ml square, ठीक है. Acha, how is it L by root 2? Oh, sorry, I forgot to tell you. You know what? How is it L by root 2? Have a look. This is the square. This is the square. And this is the axis. So let's see if I'm taking this as the mass, or concerned mass rather. So this is the mass. So I need only this much of the perpendicular distance from the axis, because this is the axis now. So this much perpendicular distance is what I need. I know that this is L root 2. Of course, yes. So it is L root 2. But what is this? This is half of that. And that's what the answer that